Is it just gonna be the notes that were on here?
Yeah.
Please tell me we're not gonna do all of those examples.
No. I'm going to do enough to get you through the homework, and then we will apply applications when needed. Tomorrow's Saturday. So Monday, I'm gonna throw them in with that one. Okay, so mean value theorem. If you guys looked at the notes, this simply says that if I have a graph, and on this graph I have 2 points, A and B, I don't know, some nice pretty curve happening. There is some point C where the derivative equals the slope of the line between A and B. So there's some C in here where the derivative equals the slope of that line. I know it sounds really confusing. When we think about
the way that you drew that and explained that made way more sense than anything on the notes.
It did or it didn't?
Did. Like
Okay.
that, I actually understand what I'm supposed to be doing now.
Okay, so mean value theorem algebraically says the derivative of some point C is equal to the average rate of change between the endpoints B and A. So our average rate of change formula is f of B minus f of A all over B minus A, where A and B are these endpoints that are the interval that C must exist on. So C is some number between A and B, and there is some point C where the derivative equals the average change between A and B, which is the slope of the line that connects them. Dana's still looking at me like I'm crazy.
I'm not sure.
We're going to do examples that'll have numbers in them. It'll make more sense. Before we do that, however, we need to clarify a couple of things, and that is that mean value theorem does not always apply. So it only applies when the function is continuous on that interval. So continuous on the closed interval A to B, and able to take the derivative on the open interval A to B.
So what's the difference between the parentheses like this?
Closed means I include the endpoints. Open means I don't include the endpoints. Okay, so it only applies when these things are true. So we have to check that these things are true before we can actually do the mean value theorem. So the example I want to start with is f of x equals x to the 2/3 on the interval 0 to 1.
Where's this at?
Bottom of the first page. Yeah, it's example A. So we first have to make sure that the function is continuous on this interval. As I'm looking at it, that's continuous. There's nothing between 0 and 1 that's going to make that go undefined. And there's obviously no jump discontinuity or removable discontinuity here, so it is continuous. And then I have to verify that it is in fact differentiable. And if you graph it, you can tell that it is. So when are functions not differentiable? Jumps, removables, infinites, sharp corners, and at cusps. So like if it comes to a point but is still curved, that's a cusp. So that is where it's not differentiable.
We have to graph it every time.
Graphing definitely helps to
Like
identify
on
that,
my,
yes.
on my calc.
Yes, you can graph it on your calculator. You don't have to plug in a bunch of points. That's way too much work. So we verified that it is continuous and that it is differentiable, which means I can apply mean value theorem here. I don't know what the C value is that I'm going to be looking for, so that's what I'm solving for in the end. So I set up, yes dear.
Okay, how do you figure out if it's continuous if it doesn't have like the brackets in?
If it doesn't, like you look at the graph. So if there's not a vertical asymptote, if there's not like a jump discontinuity, so it stops here and starts here.
Both things you have to
Graphing is the easiest way to determine that, yes. Every polynomial pretty much though is continuous as long as it doesn't have a denominator and isn't a piecewise function. That's a good rule. Yes, dear. Just the original function.
So you just like put x to the 2/3?
And then let it graph. That's all you gotta do. Okay, so now for the mean value portion of this, I just followed this equation that I wrote down. So I'm gonna do f prime of c, because I don't know what c is, so I leave it in there, equals the function solved at the second endpoint minus the function solved at the first endpoint over the second minus the first. So f of 1 minus f of 0 over 1 minus 0. F of 1 means that I'm just going to go ahead and plug 1 in for x and I'm going to solve. What's 1 to the 2/3? 1. What's 0 to the 2/3? What's 1 minus 0? So then I get 1 over 1, which is just 1. Right? Now what I have to do is I have to take this function, I need to find its derivative, and I need to set it equal to 1 and solve for x. That x then will be the c value that I was looking for. So I need to find the derivative of x to the 2/3. What's it going to be? Okay. You can leave it like that, or you can go ahead and write it as its fraction, which is 2 over 3 times x to the 1/3, right? Like I just moved the x down to the denominator with the 3.
X just becomes a C.
I like to replace it with c, that way I remember what I'm trying to find. You could leave it as an x if you wanted to, that's okay.
So
And then I just set this equal to 1 and I solve for c.
Yeah, that confused me. I was like, why did the X become a C?
Because we're trying to find c technically, so you don't have to replace, but you just so you know what we're trying to find in the end. So then what am I going to do to solve for c here?
you multiply by the 3c
To the 1/3, multiply it up
Yeah,
into
yeah.
the top, right? So I get 2 equals 3c to the 1/3. Divide the 3 back over. So I have 2/3 equals c to the 1/3. How do I get rid of a 1/3 exponent? Take it to the cube. So the whole number that's going to cancel out that 1/3 is 3. So I cube both sides. And then I have 2 cubed is 8. 3 cubed is 27. And c to the 1/3 cubed is just c. Once I get this value, I verify that it does in fact exist between 0 and 1. And it does. So this is the c value I was looking for. Well, we cubed it because it was a 1/3. And the only way to cancel out a denominator of 3 is to have a 3 in the numerator. So that's how I determined.
If it was 2/3.
If it was 2/6, then I would take it to the 6th power and then I'd have to square root at the end. Yeah. How do we feel about that? That is mean value theorem. That's it.
So what was up with the?
Well, there's like increasing and decreasing stuff in there, of course, and there are like variations to it
and
and applications, but
what's
No.
corollary?
8 pages worth of them.
Right, it's like
What?
COROLLAR.
corollary. So those are just kind of like rules.
Okay, but
That's what confused me was corollary.
So we're gonna do another one as practice. But this is all your homework is over, is identifying whether you can or cannot use the mean value theorem and then using it.
all right, let me do one.
Oh, no, really, you included.
That's because we're getting ready to start antiderivatives, that's
But
why.
not
Are you kidding?
I will not throw that on this part today. We'll get there.
I'm joking.
Not a second, we'll get there on Monday. But,
How much are we doing on Monday? Jeez.
okay, so the next one I'd like to do is the function that is natural log of x minus 1.
This is B.
This is b.
Wait, the antiderivative, that's just like taking the, like, bring it back to the original.
Yeah, we bring it back to whatever it was before I took the derivative.
I should understood.
Oh, so it's
That's either you love it or you hate it, there's no in between.
No, I actually, like, when I was writing it down, like, yeah.
Good.
That's the only thing I understood.
Good. Which is funny because that's honestly the hardest part of
Is
that.
there a theorem?
Wait.
Like,
For antiderivative?
yeah,
Yes,
like-
we'll get there. We're just not there right now. Okay, So let's do this example.
Yeah, you are.
What two things have to be true in order to be able to take the derivative? Oh wait, I need an interval.
You don't need
It has to be continuous and it has to be differentiable. Easiest way is to graph this. When we graph it, we see that it is in fact continuous and it is in fact differentiable because I have no skips, I have no infinite discontinuities, I have no sharp corners, and I have no cusps.
So how do we tell if it was?
Well, if there's no break in the graph, it's continuous. Yeah. Now that I verified it is continuous and it is differentiable, oh my gosh, I can't talk. What do I do next? What equation do I use?
Mean value.
The instant equation of change.
F prime of C equals F of B minus F of A over B minus A, where B is the second or the right-hand side of your interval, and A is the left-hand side of my interval. Because technically they're each an X associated with a different Y. That's why. So then I'm going to have F of 4 minus F of 2 over 4 minus 2. I go ahead and I plug those in. What is F of 4? It's just going to be the natural log of 4 minus 1, which is 3, right? So I have natural log of 3. And then I plug the 2 in. 2 minus 1 is 1. So I get natural log of 1 over, what's 4 minus 2? 2. That'd be kind of funny, I'm not gonna lie. Okay, so now I can go ahead and plug those into my calculator. The problem is I'm gonna get a decimal. So I don't like to plug it in unless I know it's gonna come out nice and pretty. Are either one of those gonna come out nice and pretty?
Natural log
The natural log of 1 does. What does it come out to?
0.
0. So that part goes away. So that means that F prime of C here is just equal to the natural log of 3 over 2. That is how I would like to leave it for this portion. So now, derivative of natural log of x minus 1. So what is the derivative of natural log of x minus 1? Correct. So it's just 1 over x minus 1. I'm going to replace the x with a c. That way I remember that I have to verify it's on my interval. And then I set that equal to natural log of 3 over 2. My goal is to solve for c. So what do I need to do first? What are you thinking, Lauren? So multiply the 2 to the left and the c minus 1 to the right. Right? Just cross multiply. So when I do, I get 2 equals natural log of 3 times c minus 1. I want the c minus 1 by itself, so I need to divide the natural log of 3 out. So I get 2 over natural log of 3 equals c minus 1. And then add the 1 over, and I get 2 over natural log of 3 plus 1 equals c. And then, of course, you can take the decimal from there.
Could you have taken both sides to the negative 1 power to get C as 1 on top?
It still would have worked out the exact same. Yeah. We'd actually, yeah, we'll just say that you can do that. Okay. Questions, concerns, or issues with that? Are we having major problems or misunderstandings with this?
I just I stopped paying attention for like a second. Where did the 1 over c minus 1 come from?
My derivative of f of x would be 1 over x minus 1, and I just replace the x with a c. Are you good with that, Devin?
Yeah.
Okay. So we'll do 2 more. And then I will stop and you guys can work on the homework. Next one. f of x equals the absolute value of x minus 1 on the interval 0 to 4.
Okay, absolute value makes the inside positive or makes the inside negative?
Makes inside positive.
Okay, so it would be x plus 1 or
No, so I would have to plug the x in first and get my answer, and then whatever my answer is, I'd make positive. We don't change anything the way it sits, just whatever answer I would get. What is the first thing I need to do when I'm doing mean value theorem? Check that it's continuous and differentiable. Is this continuous? Yes, it's a polynomial, which means it's always continuous as long as there's no denominator and it's not a piecewise. So continuous is satisfied. What about differentiable?
Unfortunately, it's not.
How do you know it's not?
It's our corner.
Okay, so if I were to graph this, and I graphed it, it would look like this. My interval went from 0 to 4. So if any point on there was a sharp corner or a cusp or a break, it is not differentiable. As Liam noted, I had a sharp corner at 1, which means at 1, this is not differentiable. So it fails and I cannot apply the mean value theorem. So I would just stop. This is why we graph it, because you might have done all the work and then realized at the end it wasn't going to work.
You take the derivative.
Technically, we take 2. But that's not something you're going to say in the AP test, so it's not something I'm worried about right now.
Great.
Wait, so how did we tell it wasn't? How it wasn't differentiable? Is it a corner?
Because there was a sharp corner at an x value that existed between 0 and 4. So if it existed at 0, it would have been fine, because differentiability is on an open interval, which means I don't actually include the endpoints. But if it's any value between there, it doesn't exist, or you can't do it. Questions, concerns, or issues? Okay, so we're gonna do one more example, and then I'm gonna let you work on your homework. So the next function I would like us to do is f of x equals sine inverse of x, where x is between -1 and 1, and then x over 2 plus 1, where x is between 1 and 3.
So wait, do we have an interval or is that our interval?
Well, my interval was given by the piecewise itself, so I can see that my interval is from -1 to 3. So as I'm looking at this right now, do I think that I'm going to be able to apply mean value theorem? Why not? But not every piecewise function is discontinuous. How do we check to see if it is in fact discontinuous? Okay, check where the two functions split. So what x value did my two functions split at? 1. So I plug 1 into each of them. If they give me the same answer, it is continuous even though it looks like it's not. If they give me 2 different answers and it's not continuous, then I can stop here. So I take 1 and I plug it in to each of these functions. And I find out what answer I get. So sine inverse of 1 means I need to know the angle that gives me a y value of 1. So if you know your unit circle, which hopefully somewhere in your brain, you know that pi over 2 is going to be the angle, or 90 degrees, depending on how you wanted to look at it. When I plugged 1 into this one, 1/2 plus 1 is what? 3/2, or 1.5. Are those two the same thing? No. So it is not continuous at x equals 1. So mean value theorem does not apply. Any issues with that? Okay.
Piece, like, if those were the same number,
Mhm.
would it be differentiable as well?
If that was an endpoint of the interval, we'd be able to take it, but it's no. Not necessarily anyway. We could check it by taking the derivative of each of them, but
So if the derivative and the point are the same,
Yes.
it would be.
but if it's endpoint, I don't have to worry about it because of open interval for differentiability, but closed interval for continuity. Okay, so homework's on Canvas. That's what you're going to work on. We will continue this on Monday.
We're doing the mean value.
Yes, you're still doing